What is a sequence? A sequence is a list of elements written in a definite order. For example, we have this sequence of 0, 2, 4, 6, 8, 10, and so on, which is actually multiples of 2 starting at 0. Another example would be 15, 20, 25, 30, and so on. And we can define that as a sequence of the multiples of 5 starting at 15. Another example is the sequence of -1, 6, -1, 6, and so on, which we can describe as the sequence of alternating -1s and 6. In general, we write a sequence in this way. The elements are represented by a sub 1, a sub 2, up to a sub n, where n is any integer, and these elements are enclosed by a bracket. We also don't have to write each element. We can just write the sequence of general a sub n from n is equal to 1 up to positive infinity. The elements a sub i's are called the terms of our sequence. Here we call a sub 1 the first term of the sequence, a sub 2 the second term, a sub 3 the third term, and in general, a sub n is our nth term of the sequence. Take note that in our sequence, it doesn't have to start at n is equal to 1. It may start at any integer, but usually we start at n is equal to 0 or n is equal to 1. Before we move to our main objective, let us check out some special sequences. The first in our list is what we call arithmetic sequence. The nth term of any arithmetic sequence is of the form a plus nd, where a is a fixed constant and d is what we call the common difference of the sequence. For example, we have this sequence whose nth term is equal to 0 plus 2n, where n starts from 0. We already saw this earlier. This sequence is equal to 0 if n is 0. If n is 1, we have 2. If n is equal to 2, we have 4, and so on, 6, 8, and 10. So this is the multiples of 2 that starts at 0. Another example is 10 plus 5n, where n starts at 1. So if you write this, we have 15, 20, 25, 30, and so on. We can also have a negative common difference. Here we have 5 minus 3n as our nth term. If n is equal to 0, our first term is 5. If n is 1, we have 2, and so on. -1, -4, -7. Observe that the formula for a sub n's may not be unique. For instance, in our second example, this sequence can also be written as 0 plus 5n, where n will start at 3. You can also write it as 5 plus 5n, where n starts at 2. So we can represent a sequence in many ways. Now let's consider this second special sequence, what we call the geometric sequence. Here the nth term is of the form a times r raised to n. So instead of plus from arithmetic sequence, in geometric it is times. We multiply the fixed constant a to the common ratio r. So instead of common difference, we have a common ratio. For example, we have the sequence of -2 times 3 raised to n. So here the fixed constant is -2, and since n is the exponent of 3, then 3 is our common ratio. So if we expand this sequence, we have at n is equal to 0, the first term is -2. When n is equal to 1, we have -6, -18, -54, and so on. Another special sequence is the Fibonacci sequence. The first two terms of the Fibonacci sequence is equal to 1, and the rest of the terms, say a sub n, is equal to the sum of a sub n minus 2 and a sub n minus 1. That is, it is the sum of the two previous terms. So if we write the sequence, the first two terms is equal to 1, then the next term is the sum of the previous two. So here 1 plus 1 is equal to 2. The next term is 1 plus 2, that is 3. Next term is 2 plus 3, so we have 5. 3 plus 5, we have 8. 5 plus 8, we have 13. 21, and so on. Now, our main objective for this lesson is to determine the behavior of a sequence a sub n as n increases without bound. Let's say, for example, we have this sequence 1 over n squared. Here, the first term, so when n is equal to 1, we have 1. When n is equal to 2, we have 1/4. When n is equal to 10, we have 1 over 100. Let's say if n is equal to 100, the term is now 1 over 10,000. And if n is equal to 1,000, then our term is 1 over 1 million. So here, as you can see, as n increases without bound, the terms are approaching 0. So here we say that the sequence 1 over n squared converges to 0 as n increases. So here, what do we mean when we say that a sequence converges? If the nth term a sub n approaches L as n increases without bound, then the limit of the sequence is equal to L. And we write it this way: the limit of the nth term as n approaches positive infinity is L. We say now that the sequence is convergent if the limit of the nth term exists. Otherwise, the sequence is divergent. Before we go to examples, let us consider this graph of a sub n. So when n is equal to 1, the value of the first term is represented by this dot. If n is equal to 2, we have this. And if n is equal to k, it is equal to this representation of this red dot. And if n goes to infinity, then we have these values for our terms of the sequence. Now let us consider a function which has the same behavior with the sequence a sub n as n goes to infinity. So here, it doesn't matter if the function behaves quite differently from the behavior of the graph of a sub n, as long as it has the same behavior when n goes to infinity, or in the case of the real valued function as x goes to infinity. So now maybe you are asking, why do we have to compare the sequence of a sub n's to a real valued function f of x? Well, note that we have already been dealing with functions from the start of this course, or even in our previous elementary analysis courses. So we can think of sequences as functions instead. But the difference here is, in the sequence of a sub n's, the value n that we input in our terms is a subset of the set of integers. So n is equal to 0, n is equal to 1, 2, 3, and so on and so forth. But for the case of f of x, the values of x here is inside the set of all real numbers. And we have this theorem. If this function f is defined on k to positive infinity for some natural number k, and if we input integers to that function f of n, if we get a sub n for all integer n greater than or equal to k, then if the limit of the function exists, then that limit is also the limit of our nth term a sub n. But if the limit of our function is either positive or negative infinity, then likewise the limit of our nth term a sub n is also positive or negative infinity respectively. So be reminded that for us to use this theorem, our function should be defined on k to positive infinity, where k is the starting integer where the function and the sequence coincide. A sub n is equal to f of n. For our first example, let us show that the sequence of 1 over n squared, where n starts at 1, converges to 0. So let's get first a function. Let us define the function f as 1 over x squared, where x is an element from 1 to positive infinity. Again, you may think that why do we still have to define a function if we are just replacing n by x? In our sequence 1 over n squared, the n's are integers. But in our function 1 over x squared, x is a real number greater than or equal to the integer 1. Now you may also ask, how will we know the interval where x is coming from? Here we have 1 to positive infinity. How will we know if we start at 1? Well, you can observe the function. The function is not defined at 0, and it is defined on any other number. So we can start at the starting integer n of our sequence, which is n is equal to 1. Okay, now let us just write here f of n is equal to 1 over n squared for all n element of n, or the set of all natural numbers. Natural numbers, we mean the integers starting at 1. So 1, 2, 3, and so on. Well, this is already obvious since we forced to define our function to be exactly the same as our n terms. But let us just write it anyway for the sake of using the theorem. Okay, now so let's get the limit of our function. The limit of f of x is equal to the limit of 1 over x squared as x goes to infinity. That is equal to 0. And since the limit of our function is 0, then it follows that the limit of the nth term of our sequence, 1 over n squared, is also equal to 0 from our previous theorem. And by definition, since the limit of our n terms is equal to 0, then the sequence converges to 0. Next, we consider the sequence square root of n squared minus 5 all over 3n plus 1, where n starts at the integer 3. Our first step is to define a function that behaves the same way as our sequence. So here, let us just replace n by x's, square root of x squared minus 5 all over 3x plus 1. So here, this function is undefined when x is equal to negative 1/3. But our starting integer in our sequence is 3. So we can let x to be from the interval 3 to positive infinity. Now let us get the limit of this function. The limit of square root of x squared minus 5 all over 3x plus 1. Recall from elementary analysis that to evaluate such limit, we multiply it by 1 over x raised to the highest degree in our denominator. So in this case, that would be 1. So 1 over x all over 1 over x. In our numerator, we have a square root. So if we put x inside the square root, we have x squared. So if we multiply that with x squared minus 5, first we get x squared over x squared is 1 minus 5 over x squared all over. For our denominator, we don't have a square root, so we can just directly multiply it by 1 over x. 3x times 1 over x, that is 3, plus 1 over x. The limit of this is the square root of 1 minus 0 all over 3 plus 0, or simply 1/3. Now again, we note that if we put any integer n in our f, then we have the square root of n squared minus 5 all over 3n plus 1, which is the nth term of our sequence. And since we have this condition, from our previous theorem, we say that the limit of our nth term in our sequence is also equal to the limit of our function. So that is 1/3. And since the limit of the nth term exists, then we say that our sequence is convergent with limit 1 over 3. Now for our last example, let us consider the sequence e raised to n over n, where n starts at 1. Let us define the function e raised to x all over x, where x is an element of 1 to positive infinity. This is good. F is defined here since x is not equal to 0. So x can start at 1. Now let us get the limit. How do we get the limit of e raised to x over x? Note that if we evaluate at x as it goes to positive infinity, then we get an indeterminate form, infinity over infinity. For such indeterminate form, we can use the L'Hopital's rule, right? If the indeterminate form is 0 over 0 or infinity over infinity, we can use L'Hopital's rule. That is, we get the limit of the derivative of the numerator over the derivative of the denominator. The derivative of the exponential is itself, while the derivative of x is equal to 1. So we have here the limit of e raised to x. And the limit of that exponential function, e raised to x, is equal to positive infinity. That is, the limit does not exist. Thus, by our previous theorem, since the limit of the function does not exist, then likewise, the limit of our nth term is also equal to positive infinity, does not exist. And by definition, we say that the sequence of e raised to n over n is divergent. Please try to answer this exercise. Determine if the following sequences are convergent or divergent.